Just 1 second. So our next speaker is Amir Aavani, and he will present himself much better. Please take a look.
Since I'm defending very soon, I decided to talk about what I did during my PhD. My work is centered around constructing a solver, which we call it Enfragmo. It's a grounding-based solver. So I'm going to tell you what I mean by grounding-based solver. So I'm just going to give you a big. So I'm going to tell you what a model-based problem-solving approach is and what is a grounding-based solver. And then I'm going to talk about my contributions. Very briefly, I'm not going into details of the results, or I'm going to just mention what I did during my PhD. So, given a problem, let's say we want to solve a problem. The most basic approach is to develop an algorithm to solve the problem. So if you want to do that, we need to know how to compute the answer. We need to write a program to compute the answer. But there is another paradigm, which is called model-based problem solving. In this paradigm, instead of describing how to compute the answer, we just need to describe the relation between a correct solution, the solution we are looking for, and the input to the system. And that's all we need to do. So we pass the problem specification and the problem instance to the solver. We don't need to worry. We don't need to study the heuristics. We don't need to worry about how to develop a code. We don't need to know anything about the coding. And also there is a clear separation between the problem description and problem instance. So I'm going to describe it in an example. But these are the motivations. So if you want to look at this as a logic, in logic context, it can be seen as a model expansion problem. So let's say we have a logic or a language in which we describe our problem. We tell our system that what is the relation between our solution and our instance. And we pass a structure, which is our instance. For example, if you are talking about graph coloring, our instance would be a graph, the edges of graph. For example, so here this is, let's say we are going to find a valid tree coloring for a graph, which some of the vertices are already colored. They have pre-assigned color. So E describes the edges in the graph. R of P says that if a vertex is already red or not. The same way G sub P and B sub P says that if a vertex is already assigned blue or green or red or not. And we are looking for R, B, and G such that they satisfy certain properties. These properties are described in phi. So we are looking for a model, a structure, a solution which has this property, which models phi. So it's kind of like logic, but essentially we're looking for a solution which satisfies all the constraints in phi. If you want to look at it as a non-logical term. So, but what is grounding and why we are using this? So the idea is that, so essentially there are many low-level, efficient low-level solvers. For example, there are many SAT solvers these days, or ILP solvers. They can solve huge problems very fast. But the issue is that their syntax is very abstract. So, for example, the SAT solver, they just accept CNF formula, which is, I'm not sure if you're familiar with it or not, or ILP solver, they just get a bunch of linear constraints. Expressing a problem for them is kind of hard. It's not straightforward, at least. If you know how to do that, okay, you can do that. But if you don't know, you're not familiar with the system, it's really hard. If you want to develop a grounding-based solver, you can look at it as a system like this. So we pass a problem description. This is our file. This is the problem instance for our graph color. This is a graph age, and it has three main components. The first part is a grounder component. It gets the problem description and the problem instance and generates a CNF or an input to a low-level solver. It can be anything, but right now in our system it's a SAT solver. So our grounder creates a CNF formula, pass it to our low-level solver. The low-level solver tries to solve its input CNF, and if there is a solution, it passes it to the translator. The translator, if there is any solution, converts back the solution to the original problem. That's the basic idea. So essentially, we have three components. So the translator is very easy. This low-level solver, again, is not, so in my work, I don't worry about the low-level solver. I'm looking at it as I can use any off-the-shelf solvers. So it's a plug, I can take it out and plug in another solver. So essentially what I'm going to talk about is how I'm converting the problem instance and problem description to an instance of a SAT instance or CNF formula. So essentially, so to describe a system like this, we need to talk about its input language first. So how we can describe the problem. The input language of Enfragmo is an extension of first-order logic, in which we can use function, aggregates, inductive definitions, and arithmetic terms. So essentially we have everything as we have in SQL, and even more, we have inductive definitions too. So essentially it's a rich language. And we have two phases to convert an instance and input to the CNF. The first phase is grounding phase, or I wrote grounding module here. It gets the input and generates a variable for the first order formula, and then we pass it to makeCNF module. The makeCNF module gets a variable for the first order formula and generates CNF instance. So essentially we break the grounding phase in two phases: grounder module and makeCNF module. I'm going to just briefly go and talk about them later. Yeah, and so essentially the third phase, which SAT solver to use, is kind of, again, Enfragmo right now can select automatically between three SAT solvers. But I'm not going to talk about that right now. So the language of I'm going to describe it, explain it as using an example. Let's say we want to describe graph coloring, graph tree coloring. So we want to assign, so the first axiom or the first rule says that for all V, for every vertex, it's either red or green or blue. It should be colored with one of the three colors. The second one says that if a node is colored red, it cannot be colored green, or it cannot be colored blue. And the same, we have similar rules for the blue and green. And also we need something like this. If there is an edge between U and V, they can both, one of them should be not red. And the same way we need similar rules for green and blue. So here, as we see, so the blue things are describing instance, and the red are describing the solution. So if we can expand A to structure B, which satisfies this formula, we have a solution, a valid tree coloring for the graph. Okay, so from Okay, it's a well-known fact that existential second order logic can captures NP, meaning that we can describe every NP problem, such as graph coloring, Hamiltonian cycle, and most of the scheduling or planning problem using this logic. But it's not straightforward to do so. So if, for example, if you have arithmetic or we have rituality, it's not really easy to describe these problems in existential second order. It's kind of like, it's going to be very messy. So that's why we decided to enrich our language with arithmetic, aggregates, and inductive definition. These constructs enable us to describe our problem more efficiently. And also, we wanted to stay in P. So I'm not gonna talk about that, but we add these terms, we expand our vocabulary, we have an English language, but still we are still in P. The next thing I did was to develop some ideas and strategies for developing easy to solve specification. So, for example, breaking the symmetries, or making search spaces smaller, using upper bound and lower bound, and using inductive definitions. These things can help us to solve the problem more easily. So essentially, they don't have a lot of overhead, and they don't cause a lot of overhead for our grounder, but it makes the task of solving much easier. So let's see an example, and I guess that's going to be more easy to work. So let's say we're looking at the social golfer problem. We are having G times S golfers. They are playing in G groups. Each of the groups should have S golfers in it, and they want to play during the W weeks. So it's like, I don't know, it's like a game. So yeah, so let's see how we can encode it using our rich language. So we want to say that each group must have S golfers in it. So I'm saying that the number for each week and group, the number of golfers in that group should be exactly equal to group size or S. And so we want to say that every two golfers should be there should be groups such that for every two golfers, there should be exactly one group they have been in it. So we're saying that for our two golfers, there should be, okay, I forgot to say it, MWGP means that the golfer P will play in group G in the week W. So I'm saying that the number of weeks and groups such that P1 is playing that group and P2 is playing on the same group should be 1. So it says that, okay, there should be exactly one, for each two golfers, there is exactly one group that they're playing in. And the last one says that, okay, in each week, every golfer should be playing in one group. So this says that, so this is the basic the specification for social golfer problem. But we can add some extra constraint to break the symmetries and make the solver, to make the search space smaller and also make solving easier. So for example, we can say that the first golfer, the golfer number 1, should be always in the group number 1. Okay, I mean, so it can be everywhere, but we are moving it to group number 1. Or we can say that we should, there are some optimizations that they are easy to see, but I'm just describing them, but not going into details. So for example, we can say that the groups can be ordered for a given week. The groups can be ordered based on the index of the minimum player in the group. So for example, here I'm saying that for if group 1 is less than group 2, then the minimum golfer playing in that group 1 should be less than the minimum player playing in group 2. And we can assess something similar about the second smallest player in the group. So by using this approach, we can break lots of symmetries and make the search space much smaller. Okay, so So to do the grounding, what I did was, so I defined an extended relation, which is kind of like the extended relation using the relational algebra. I defined, for each Boolean operator, I defined how we can compute the answer for that operator, and then we can construct the answer recursively. And do I have any time? Can I? Okay. So I described how we can handle I said that we enrich our logic with complex steps, more complex steps. So to handle the complex step, I used a similar idea. I defined new extended relations. I defined some new answers. I extend the relational algebra I defined previously to be able to work with the new extended expressions. And then I'm constructing the answer for terms recursively. And since the terms can occur in the formula, in the atomic formula, I need to somehow connect the answer to terms and answer to formulas. So these are done, and so our system right now can ground complicated formula, complicated specification to a variable first order formula. Okay.
Just finish your speech.
Okay, so essentially, we have my CNF phase, which I'm not talking about it right now, and so essentially I briefly presented our solver, which is called Enfragmo. It converts the specification to CNF formula in 2 phases. I tried to describe the grounding phase, and the make CNF phase I haven't described that yet. But our experimental result shows that it performs much better than IDQ or DLV, which are 2 well-known solvers which work based on a similar idea.
Okay, so let's thank our speaker. And we welcome one question from the audience. So, any specialist in their area or want to know more? So, come on, ask a question. Any?
Okay, don't have me.
Okay, so anyone? I have a question then. I will ask a question. So, with your solver, do you have any documentation? Like, did you make a package or make it open source?
It's not open source because of the licensing issue, but yeah, that's a good question. So we have manual for it, but it's not up to date. Yeah, I mean, you know how it works. So essentially, it's developing every day, and so we add a new feature to it, but it's not documented yet.
And maybe to follow up, so you're saying that you are about to graduate, but do you think your group will continue to work in this direction?
Yeah, but that's a good question. I'm not sure. I guess they like to work on it, but I'm not sure if they're gonna do that or not.
Okay.
Let me ask a question. I just don't want a chocolate, so that's why I don't want. I don't want a chocolate. I'm actually
Okay, sure.
get a chocolate. You can get it. Obvious question would be that you're a studying language, right?
Yeah.
Do you have any proof as to whether this language is complete?
So yeah, essentially, I've proven that this language can express all NP problems.
Right.
So you can express every NP problem using this language,
Okay.
and whatever you can
But
express.
it is not minimal then.
Sorry,
It is not minimal.
it's not minimal.
Minimal in terms of sometimes they use the number of instructions in a set to show whether it's minimal or not.
So essentially, given a problem, you can describe it in many ways. So I mean, I'm not sure how the term minimal can be described here, but essentially we enriched. So as I said, for the new construct I added to the language, so I added them to make the problem specification much easier.
Okay,
So
it's more efficient.
yeah, it's much easier, not efficient maybe.
Much
so,
easier.
So a user can more easily describe their problem. That was one of our main goals.
Let's thank our speaker. I think it was a wonderful presentation. Thank you a lot, Amir.
Thank you.
And we have